I'm going to try to make this part of the talk a little lighter than some of the previous ones. I know that since we've already covered a lot of sandboxing, some of the material I'm going to have in my slides you've probably just watched about 30 minutes ago. With that in mind, I'm going to come to some conclusions in my slide that I think are still valid, but Ian did a pretty good job of trampling on some of them. Thanks. I have a background more in reverse engineering and malware analysis, so I'm going to take a look less from the vulnerability research side of Mac Sandboxes and actually see how do malware authors interact with the Mac Sandbox and dive pretty deep into what that looks like on the systems. So you're pretty familiar with downloading software on the internet and how that's sort of the wild west of who knows what you're going to get. You might be thinking you're getting a piece of antivirus software that's actually installing viruses. You might think that you got a little flashlight app on your iPhone that's actually emailing your contact list out to remote servers. So based on what surprises you're finding here on the internet, a lot of people are upset with how that security posture is handled on their devices, and they want ways of controlling the security of their devices. A lot of this stuff we were just talking about with sandbox escapes or the more advanced versions of that sort of thing. But you can have much more basic things of it just pops up ads and is annoying. It just takes your files and sends them off somewhere for scraping and stealing identities. So some of the security controls, guys are probably all familiar with a lot of these. And these, if you've run Mac systems for a long time, you've seen these grow. Things like privilege separation, where when you log onto the system, you don't automatically have root access, was not always true on Mac platforms if you go back to the original like OS System 8 and System 9 releases. Some of these other ones that we've already talked about today as well. Signature checking is a great way that when you download a piece of software from the internet, of knowing who created it, are they who they say they were, was this altered as it traveled through the network. Some of the hardening things that once your operating system is running programs to say, is it doing valid deserialization? And even though we've seen a lot of defects in these categories, even some that were just presented today, I think we can agree that the systems have gotten a lot better from some of the previous defects we've seen in them. Some of the ones I really want to drill down on here today, though, are behavior-based limitations of software and also containers, and the way those kind of combine together into what the Mac Sandbox infrastructure looks like. So behavior-based limitations are details of what you expect a piece of software to do. For instance, you expect your flashlight to turn on the LED. You don't expect it to read your contact list. And containers are the way that an app can see the entire state of your computer, whether it's all the files on your file system, talk to any of the other programs, and grab personal information. So by taking an app and placing it within a container, you prevent it from getting access to all those other parts of your system and stealing your data, which you've seen a lot of ways of getting out of. So mandatory access control specifically, this is how Apple has created their sandboxing implementation. And it's sort of an older concept if people have been doing security for a long time. You might be familiar with some other versions of this like SE Linux and AppArmor. Apple has chosen to base their design on trusted BSD. And what this basically does is whenever your piece of software is running and it tries to get the operating system to do something for it, the operating system is going to say, are you allowed to or not? So if you say, please open a file for me, it'll say, is this a file that I should allow you to have access to? Additionally, if you write a piece of software that handles your files, the mandatory access control in the containers will prevent you from accessing the files of your neighboring apps that weren't developed by you. Sort of an aside here, looking for all the source code, and you can find a lot of the source code for mandatory access control in the XNU source published by Apple. Grepping for the string Mac in an operating system called Mac is sort of a pain in the butt. So a bit of the history of the Mac Sandbox. It wasn't actually always called Sandbox. Originally, this was called Seatbelt, which had the exact same initials. It was first introduced in the Leopard version of the operating system. And the analogy the marketing guys are trying to make you think about is that the sandbox is like a safe little place for your apps to play, where you don't have to worry about what they're doing, and the whole thing is nice and happy and safe. And so currently the way this is implemented on the Macintosh, and this was some of the stuff that Chris had talked about, is based on top of all of your files having code signatures, Gatekeeper making sure that your signatures are enforced, and the App Store having a person that audits all of your files to make sure that those signatures and behavior controls are sane. So specifically code signing, this is a cryptographic signature where only the developer is able to claim ownership of his code, and no one else can impersonate that developer without stealing his credentials. We actually had a whole bunch of discussion on Gatekeeper already, so I'll give you the quick summary of this one again. This is the feature within your operating system that says you can run whatever you want. You can run stuff that came only from the Apple Store, or you can choose to run stuff that came from the Apple Store or whatever else that you feel like downloading that has a signature. And lastly, the App Sandbox policy here, the App Store Sandbox policy, there's an actual person here that's going to read all of your sandbox controls and decide, like, hey, does this piece of software have a sane set of sandbox rules, or is it asking for ridiculous things? And that person will simply reject delivering your app on the App Store if he doesn't feel that that's a good idea for the customers. Gatekeeper. So the default behavior here now on modern versions of Mac has Gatekeeper only allow signed code, stuff that came from the App Store or stuff that you downloaded that has a developer signature associated with it. We've seen some examples of how you can get around that. But basically, if you want a piece of malware to end up on a lot of boxes, you either have to trick the user into turning off Gatekeeper or bypassing Gatekeeper, or otherwise get your code signed. Since Apple can revoke any code signatures, if you have a signed piece of code and you get it into people's computer and it starts infecting them and doing malicious stuff, all Apple has to do is revoke that signature, and a bunch of that software will stop working unless you've done other tricks. The real analogy when you talk about a sandbox is really more like a jail for your programs to live inside of, where they can't do anything that they're not permitted to do. And that doesn't specifically keep them safe from malware. It simply means that if your app is locked up in this jail cell and it gets hacked by a piece of malware, the malware lives in the jail cell next to your app, and it's going to have the ability to damage any parts of your application that it wants to within the limits of the jail cell itself. So some typical limits of an app sandbox. Some of these we saw for the iOS applications. An application will be given a couple of temporary or personal folders inside of your home directory where he can read those files but can't look in the similar subfolders of any of the other applications that are also running in sandboxes. You can't typically see arbitrary processes, even though we've seen some of these details where you can ask for the launchd, for instance. But in a typical file, you'll be restricted from sending arbitrary messages to processes. And if you were running inside of a sandbox and weren't allowed to see other processes, they wouldn't show up in your list if you ran something like PS. They just wouldn't be visible to you. Some exceptions to this: if a user decides to allow an app to have files, he can choose to say, this sandbox now includes everything originally described, plus these new files that I'm giving it access to. But other types of limits would also include things like whether an application is allowed to send and receive network connections, whether it's allowed to do things like interact with your camera, interact with your microphone, or even talk to your iPhone. Beyond that, there's some limitations specific for the iOS version of the sandbox, where it can't change memory protections, for instance, to have writable and executable memory, which ends up being the reason that you have to do all of your ROP chaining all over the place inside of your iOS exploits. And this last one, this is actually something that Ian had spent a lot of time talking with just now. In order to send a mock message to someone, you need to be able to look up their task and get their ports mapped into your process. And sandboxes can restrict which mock tasks you can look up. So for instance, if you have access to font D, all of those messages are an open attack surface for you. But if mock D is not allowed within your sandbox, then that's just not an attack surface possible for a piece of malware. Now, Apple's actually done a pretty neat job of sandboxing, and I have some slides later on where we contrast the other styles of sandboxing. When you want to configure the limits on your piece of software with an Xcode, you basically just get to pick those little toggle buttons to say, my piece of software is allowed to talk to the watch kit, or it's allowed to talk to health kit, or it's allowed to talk to the network. So you don't have to worry too much about the actual implementation of how the sandbox works, which way down at the bottom ends up being scheme files. Has anyone programmed in Scheme? List function? Okay. But the number of people that have written code for something like an iPhone or a Mac desktop, none of them had to worry about whether or not they had to learn Scheme to get this stuff to work. The way Xcode ends up making this all work, and we saw some of this for Chris's demo, is that you take all of your code, you sign it with your developer ID, you drop your sandbox description into the file, and all of that, when you decide to deploy it on the App Store, gets sent off to Apple, and they can take a look at the entire assembly, that whole bundle of code, to say this, every binary within this bundle is limited by some kind of sandbox, and the sandbox rules are appropriate here. So once you have your program up in the App Store, someone's downloaded it, and they're running it in user mode, the program will try to do normal stuff. It'll talk to the operating system, it'll make syscalls, it'll send mock messages to tasks. Each one of these is then going to be handled within the context of the sandbox. So the little piece of entitlement or the scheme file is appropriate will get compiled down into a bytecode and kicked up to the operating system, where the operating system will parse these things out. So that if the operating system says you're allowed to read this type of file and the app tries to do it when it's not allowed to, you simply get an error saying you're not allowed to do that sort of thing within the context of the sandbox. And the way that happens is up inside the kernel, every one of your syscall entries has a call out to something called maccheck. And what maccheck will do is for all of the sandbox entitlements you have associated with your app, it will say, does the first one allow you to do this action? Does the second one allow you to do this action? Until someone either says yes, or you've asked all the entitlements and no one has said yes, and typically that means that you're not allowed to do something. This is all handled up inside of the kernel in something called the Sandbox kernel extension. So I said a couple slides ago that you can read all the source code for the XNU operating system. It's all published under the Apple open source license. The Sandbox kernel extension itself is not open source, so if you want to understand this stuff, you have to go reverse engineer it. For some of that, Snare has already done some really cool reverse engineering of this stuff, so if you want to see some of the details of how that bytecode gets parsed up inside the operating system, he has a really cool set of slides you can go take a look at. So visually, when your app is running inside of a sandbox and it tries to do something here, you can see where it asks for a syscall or a operating system service. And then before it gets handled, this Mac checker will go and ask the sandbox to descend through that list of all the registered sandbox entitlements. If any of them, for instance, say you're allowed to touch any file under /home/star, the regular expressions will get kicked over to a second kernel extension called the Apple Match kernel extension, which handles all those regular expressions. And if it turns out that you're not allowed to do a certain thing within the sandbox, you'll get a log that flows back into user space, into the sandbox daemon. When I had initially started doing some of this research, I thought sandbox D was a much more integral part of the sandbox implementation, but it turns out it's mostly a log writer out in user space. But if you are allowed to do something, you have line 4 here. It just comes back and says, yeah, it's cool, you can do whatever that action is, and the action actually takes place, whether it's opening a file, returning a file handle, reading bytes, or whatnot. So this is what a sandbox file looks like. This is all written in Scheme, and you typically don't have to worry about this sort of stuff if you just use the typical Xcode interface. So I'll walk through a couple of these lines. You can see there on line 2. Is that sort of visible in the back? Is it all right? All right. So on line 2, you see that a default behavior is that if I don't explicitly allow you to do something inside of a sandbox, we're just going to decide that that's denied. And that's a pretty good design decision simply because if a brand new interface comes out and I forgot to deny it from you, it might give you additional privileges that weren't backported into an older sandbox file. I know this is very tiny, but this is all the sandbox file for the photo stream agent. So this is actually a sandbox file that Apple wrote for one of their own applications. You can see where it does allow a couple things. It allows you to read some files. It allows you to make outbound network connections. You can use the syscontrol interface to get in and out of kernel space. And also you're allowed to send Apple events, but only to one destination. So that was one of the IPC things we talked about, or that Ian had mentioned in his presentation. Beyond that, you're allowed to do shared memory through POSIX as an IPC. But for the most part, let's see. Actually, mock task name is pretty much an open door here, where if you can get the task name of another mock process, you can send it any messages you want. So that sort of allows you to do almost anything. And if you had asked for this permission through the Apple App Store, once they saw you asking for that permission, they'd simply say, no, you're not allowed to do that. Nobody's allowed to send arbitrary messages to anybody they want to. And I know before I was saying you're only able to, for instance, exploit the font service if you have access to it. But a lot of those attack surface interfaces, like the ones that Ian had been discussing, are allowed, even in this case where your photo stream software should be mostly limited. It's still allowed to talk to most of IOKit, which is all of your frame buffers, your rendering, your graphics acceleration. So there's still a really large attack surface, even though that this process is living inside of a sandbox where most things are denied. And I bet if you fuzzed some of these, you'd find even more exploits in these interfaces here. A sort of comparable interface, if you're more familiar with Windows, is all the GDI32 parsing that happens on Windows is very similar to what you're seeing here in the I/O frame buffer and the Apple graphics controller stuff. So a lot of the attack classes you would see for like a Windows GDI32 attack would be appropriate inside of a sandbox like this one. This is a whole bunch of files that are explicitly allowed, in this case for writing. Some of the ones that you would expect to see in here, the photo stream is allowed to talk to all of its own preferences. You can see the iLife photo stream about 2/3 of the way down around 46. But it's also able to do a bunch of other things that you typically wouldn't see in an App Store deployed app. This one's allowed to read whatever it wants from the calendar. And it's also allowed, I don't know if I had it cut off on the slide here, but it's allowed to read the calendar and send messages off to the mail service, which would be sort of a weird thing to do from inside a generic sandbox. Oh, this might be the slide I was referring to. There it is, right there, line 79. You're allowed to look up the mock ID for the font server and talk to it. But the takeaway from looking at slides like this is that for all the millions of things that you can do on a typical Mac computer, you're only allowed to do, in this case, about 79 things. The concept there is to prevent your app from having just arbitrary control over the entire operating system, especially in a behavior limiting context. The photo server, the photo stream program was not allowed to act as a network server, for instance. And that's what you would expect. You don't think it should be serving up web pages. So if you're coming at this from a developer standpoint, you might have the opinion, why not just allow everything? Because anytime I have to go add a new feature to my software, it probably is going to violate a sandbox rule, and then I'm going to have to go fix my sandbox file, and I'm going to have to recompile everything twice, deploy everything twice. It's sort of a pain in the butt. Why not just say default allow? That's right. The typical sandbox design discussion says that you should actually, instead of allowing everything, store a bunch of your stuff in XPC interfaces. I have in my notes here, and we've just seen how crazy it is to parse out XPC interfaces. If you didn't have to worry about writing all of that parser code, it would certainly be a lot easier for all the developers. And the reason that you don't typically get permission to do whatever you want is because the App Store policy, the guy that's going to go and audit your sandbox file, is just simply going to say, no, you're not allowed to do it that way. This is allowing you to do too many things. I know I'd mentioned the example before of a flashlight app that's able to read your calendar and make network connections. Some of the other stuff, has anyone deployed apps on the App Store since about 2013? I know a couple of you must have. There was a lot of apps that simply can't live underneath this jail restriction, where there's stuff that they want to do and they're no longer allowed to. So if you had, for instance, written something similar like Dropbox, where you would say, go take all these files and back them up for me, but those files don't live in your sandbox, and there's no way for you to get access to them through the typical sandbox entitlements in the App Store. Apple has done a little bit of a workaround for that. They have something called temporary entitlements. And when developers had first seen this, there was a lot of sort of uproar around it, simply saying, there's no way for my software to succeed if you take away this temporary entitlement. And Apple's had sort of a sane reaction to that. These temporary entitlements might not be the final implementation of an API, but over the last about 3 years that these have existed, they haven't just gone and squashed a typical temporary entitlement. They've always used it. They've always used it as a way to move forward into a permanent implementation of a useful feature. So if you're a developer and you're developing inside of these sandbox jails, it starts to feel like your world is really small. Some of the stuff that used to be really easy for you is now sort of a pain in the butt. You get this sense that, like, you're there living in your house, but everything's just not quite the right size for you. And really, that's on purpose. The whole goal of this is to reduce the attack surface so that guys like Ian have to go try at least 4 hours to go find an exploit to get out of a sandbox. And I'm going to, in the second half of my talk about a lot of the malware that I analyzed working within sandboxes. And a lot of the malware doesn't succeed as well as some of the guys that are talking here today. So the act of reducing that attack surface has actually made a lot of computers safe from the malware that I've been able to analyze. Here we mention XPC again. So the design intention of XPC, at least within a sandbox context, is that you're allowed to have several apps running inside of your sandbox, and they don't all have to behave under the exact same set of rules. So if you are the rendering engine within Chrome, you can put yourself in a very, very restricted sandbox in one situation where you can only talk to Fonty, which even in this case I guess wasn't enough. But if you had a normal payload and you just want to say, hey, I got EIP, I'm running inside of Chrome, I just want to start writing files and gaining persistence and doing whatever, you're not really done yet. I heard the term like trash bugs earlier in the day. If you have a link in your exploit chain of getting code execution, but for instance, your program is running inside of a very, very restricted XPC process, you're not home free yet. You now have to make another link in your exploit chain saying, how do I get myself out of this XPC jail? And the design concept is that you would have your most dangerous code running inside that tiny XPC jail. So if you were running Flash or Adobe or some kind of JIT interpreted code, that code would live within the least privileges possible and would simply send XPC messages back to get any other kind of work done. So for some of the malware I was looking at, I really wanted to see, can you hide within a sandbox and still get it sent through the App Store? I didn't actually see this crab until it started moving around because its camouflage was so cool. And the typical policy within the App Store is that if you send a bundle up for a distribution, they're going to go and take a look at all the files in there. If you've got Mach-O files, whether they're fat files, skinny files, PowerPC, or I guess no one runs the PowerPC Macs anymore, but also things like script files, every single one of those needs to be signed with your developer ID, and they need to have a sandbox profile associated with them. Ways of hiding, getting around that, since you can't stuff a regular executable that doesn't have to behave inside of a sandbox. On iOS, you would simply say, hey, why don't I just download my stuff later and execute it in memory? In the case of iOS specifically, you're not even allowed to allocate a big block of memory, write your code into it, and execute it. You are allowed to do that on OS X, the desktop version. But it's still a much trickier way of saying, I tricked the end user into running this code. They scanned it when it entered the machine, but I was still able to get more stuff into it later on. You have to jump through extra hoops now. So for preparation for this talk, I went and tried to find all the bad guys, all the malware that's working inside of sandboxes. And I found a whole lot of malware that didn't even know sandboxes existed. And a lot of this you can see is a couple years old. One of the ones you're probably familiar with, Flashback, came out in 2012. And this was a Java exploit. In this case, it has no signing. It has no sandbox. It would never be deployable in a typical Gatekeeper environment. The only way this code can continue to succeed is you download it, it says, hey, I'm not signed, and you have to jump through a hoop. You have to trick the user through social engineering into installing it anyway. So you're not perfectly safe from malware, but you at least have one more chain, one more link in your exploit chain. Did anyone have trouble with Mac Defender, Mac Protector? This one just came up in the news again yesterday. So Mac Protector would do social engineering. They would pop up like a little, advertiser banner in Safari and say, hey, we think you've got 47 viruses. Click here. We'll install some software to fix it. It says, out of the 47, I'm going to fix 5 of them. Now you got to pay me money to fix the rest of them. And instead of really fixing anything, it just goes off and starts serving up more internet ads so they can make money doing that. These guys just got sued on Wednesday in a big class action. I remember reading a lot of the commentary on that. These guys are in like Ukraine, and no one really thinks they're going to show up for court if they get judged against. Some more software. I found a whole bunch looking through VirusTotal and Contagio. I found samples of a virus called Kitmos, and I didn't find any description of what it does, but it does not have a signature, it does not have a sandbox, it would not run with inside Gatekeeper. I found some other ones, Nictana here. This is another ad spammer. This finds Safari, jams itself into the Safari process, and serves up a whole bunch of ads. Same deal, Gatekeeper would have a problem with this. And also Yantu, which is another virus for Mac. A lot of these coming from 2012 did not need to live within sandboxes, so it's not too unusual that they totally ignore that as a concept. But a lot of these are now mitigated through Gatekeeper without using some of the extra exploitation steps that were presented today. So the one that was most interesting from a sandboxing perspective here is WireLurker. And I think, was it Pat who already talked about WireLurker a little bit? I know I've seen its name up here before today. WireLurker actually has an entitlement file where it describes its sandbox rules, and it needs this when it gets its initial execution on your iPhone. So this is the one example of Mac software, Mac malware, where I found it participating within the sandboxing environment. And you can see where it actually puts itself into a group of applications, and if you have multiple components of WireLurker installed on your system, they're all allowed to talk to each other using that identification string. The line right below that, get task allow is true, means that it can get any task ID of anything on your system, which allows it to send mock messages to any port it wants, which basically means it's allowed to do just about anything it wants to do, which would not have gotten through the App Store vetting process, but in this case, it's right there. What I'm really surprised about, and what I was expecting to find and didn't, was apps that will attack a Gatekeeper-enabled desktop break out using any of apparently the 100 techniques that exist. And then just, run all over your system and do cool stuff. I didn't see any. And one interpretation is that there's enough users out there that don't have Gatekeeper turned on, or enough people with older operating systems, or simply enough people that will download an app off of BitTorrent and run it even though it's sometimes a bad idea. The other interpretations I get from this, and from my role in malware analysis, the expense for a bad guy to create a piece of malware grows with every little trick they have to do. Where if you need to get a JavaScript exploit to get yourself loose inside of the rendering process in Chrome, and then get an information leak to know where to drop your op chain, and then get a sandbox escape to get out of fontd, and then possibly elevate to root, which I guess all Macs have an open root elevation exploit right now. But every single one of those steps, you still have to do it. And in some of the cases, if you're missing simply one link in that chain, you don't have a viable exploit to get your code executing on the system. So if you have it missing, you might actually be able to sell the links you do have to somebody else who has the complementary ones. Alternatively, you might try to buy the links that you're missing from somebody else. And where that really becomes important from an economics perspective is if I'm trying to install spamming software on your computer and I get a penny per imprint and I think I can install it on N computers, what's N got to be before I can start making money? And if I do all the work myself, N can be 1 or 0, it has to be pretty low. But if I need to go buy a $100,000 sandbox escape, I guess a lot of them are available now thanks to your talk. But before today, there was much fewer of these out in the wild. You now need to take that into account on your bottom line. Like if I'm going to be in a crime business and I want to make a bunch of money serving spam or messing with users' computers, tricking them into sending me their credit card information, then I now need to get above a threshold. And at least in the versions that I've seen, nobody tries to actually escape from the sandbox. They're willing to sort of feed on the scraps underneath it, where they'll try to social engineer you, they'll try to get their apps side-loaded, they'll never get mass distribution through a normal chain like the App Store or something that would be compliant with Gatekeeper. So if you got your app living inside a jail, what are some of the limits, and how do you sort of test those limits, see if you can escape? A lot of the previous sandbox escapes, you guys have probably heard Charlie Miller's talks. Core had a similar extension to his original sandbox escapes. So he basically would just write a file to the disk, and in Charlie's example, get launchd to run it. You're not able to do that anymore. Core followed that up by saying, if I can send Apple message events to other processes, I could send one out to AppleScript and get it to just run a script for me. That's actually a pretty cool way of patching they did for that one. If you have an Apple script that you'd like to execute from within your sandbox, you actually have to include it in the bundle and sign it so you don't get access to arbitrary Apple scripts anymore. And when you send it up to the App Store, they can audit that alongside the rest of your code. Some of the other ones we've seen in the past, jailbreaks included HFS file system, parse corruptions, font rendering, about 70 other things within XPC now, I suppose. So escaping from your sandbox, I don't have any sandbox escapes for my presentation. I think we had several already spoken with today. Thank you. Some of the stuff that I had in mind before hearing about all your progress, a lot of the BSD syscalls have been fuzzed, but in these, there's a lot of other interfaces for getting access into the kernel, even living inside of a sandbox. And Mock, which has all the complicated MIG IPC parsing, is one of the ones I had suggested here. And additionally, IOKit, which is a large portion of the available kernel attack surface, has not had nearly as much attention as the BSD syscall. So if someone had an exploit that they had brought over from experience on Linux, BSD was the first place they looked, but I haven't seen anyone specifically banging on the IOKit interface. So even though you have your app living inside of a sandbox, that doesn't mean you don't have any bugs. This one's actually already been mentioned today as well. This is the basic root privilege escalation. Apple has tried to fix this on 10.10, refused to fix this on any previous version. So if you're not running the most up-to-date edition of the operating system, you're guaranteed to be vulnerable to this. I guess you guys were saying that even if you are running the most up-to-date version, you're still vulnerable to this. But one advantage of living inside of a sandbox is even if you're user ID 0, you still have all the limits of your sandbox. So if you wanted to read an arbitrary file, you're still not allowed to within the sandbox. You still need your sandbox escape. That's a lot of talk about sandboxes. I actually have a little bit more time, so I'm going to jump to some of my extra material here I have at the end. So in contrast to Apple's implementation of sandboxing, it's not a new concept with mandatory access control. I think it's been around since Air Force Research was trying to put this in Multics like 30 and 40 years ago. So this is a code snippet from AppArmor. This is one of the alternatives for sandboxing. This is the one that Ubuntu, Debian, all the Ubuntu derivatives use. And one of the first things you can notice from this sandbox, apart from the super tiny name of the file, this is a sandbox for Firefox. This is the default sandbox that you would get if you're running a brand new version of Ubuntu LTS. That very first line, the author, this guy, Jamie Strenboge, he doesn't work for the Mozilla Foundation or Firefox. This is a guy that works for Canonical. And the biggest ecosystem difference between the Apple Sandbox implementation and everything else is that Apple makes the developers build their sandbox configurations themselves. So in this case, Jamie, who might be able to check code in or submit bugs against Firefox, isn't a normal developer, and he doesn't have to force Firefox to comply to these, reasonable rules for them to deliver their code. In fact, this sandbox is actually disabled by default on Ubuntu. You have to actively go and turn this thing on. But right away, let's take a look at some of the lines in here. On lines 3 and 4, you're allowed to do pretty much anything you want on the internet. That's actually reasonable for Firefox. But down here on lines 7, 8, 9, you're not allowed within the Firefox interface to damage your own plugins. The Zool Runner add-ons, Firefox add-ons, these are where all the plugins for the Firefox process lives. I was really surprised with lines 10 and 11. You're not allowed to use Firefox to update your Linux kernel. That's what those lines specifically describe. Line 11 right there, that's your Linux kernel. You think your browser would be allowed to do everything. But this is the real conflict that you see in everybody else's sandbox implementation. We've got lines 21, 22 here, where we're allowed to do some limited stuff within the user file system and some limited stuff within the optional file system. You're like, okay, this file was much larger and I trimmed some of the lines out. But you can say, that looks kind of reasonable. You know, if I'm in my browser and I want to go save a file someplace, or if I want to open a file or do something like that, okay, maybe I should be allowed to read in the user file system. And then they've got lines 27 and 28, where they say, in addition to being able to read user and opt, you are also allowed to read absolutely everything. And this is the real conflict we find when a third party shows up to write a sandbox implementation, is they have no enforcement. There's no sanity check that says, like, is that an actual reasonable thing for your app to be doing? And if you were going to go ahead and write lines 27 and 28, why have the entire rest of the file? It just doesn't make a lot of sense. And the way Apple handles that is a lot more elegant. So in the sandbox descriptions I've shown, the developer at compiling and prior to deployment, he needs to explicitly label each of the directories that you're allowed to see within a sandboxed file system. So if you're a regular user and you want to just open a regular file, conceptually you wouldn't be allowed to do that unless the developer knew its name prior to deploying the file. So Apple's actually done a pretty neat thing to allow that to happen, and they have something called app-scoped bookmarks. My next slide, the other half, is something called document-scoped bookmarks. And what an app-scoped bookmark is like a temporary entitlement token saying, this process is allowed to do one extra thing on the system that wasn't explicitly allowed within my original sandbox description. So if you've done some programming on Mac, you might be familiar with the NS Open Panel, NS Save Panel GUI widgets. These come out of the AppKit assembly within the operating system. If you want to open an arbitrary file, you would just call this. You might suggest, like, hey, I think you should open your kernel file. I think you should open your temporary file, whatever. When you call this within a sandboxed program, you don't actually get the GUI widget that you expected. You get something called the PowerBox. The PowerBox looks identical to a typical open panel or save panel, but it's running outside of your sandbox using IPC. And when you interact with this, it doesn't hand back what you would expect from like a file handle. It actually hands back one of these bookmarks saying, here's a little crypto signature saying, this guy's cool, he can touch this file that he's not typically allowed to. And the typical attacks you would expect to find against something like this, like, can I suggest a file and throw a race condition where I say, you were just about to click OK on the file you wanted, and I'm going to sneak in with a file that you didn't expect. You're not allowed to send any of those messages to this GUI widget like you could in a typical one. And what's additionally cool about that is once you get these crypto tokens, you can actually save them, and the next time you restart your application, you can reopen all the files that you were able to see last time. So from a usability perspective, you almost don't notice that your app is running in a sandbox because it can open anything you tell it to, and it's not as restrictive as the AppArmor one, for instance, where if it didn't have a specific exception within its AppArmor config, it would never be allowed to touch a file outside of that config. The other half here, the document scope bookmarks, these are what allows like a static file on your file system to do the exact same thing. And if you have, for instance, a PowerPoint presentation referring to a bunch of graphics on your file system. PowerPoint's not running inside of a sandbox in this case. But if it were, the next time I opened my PowerPoint slide, it wouldn't be allowed to see all these files that were stored someplace else. So it would use this feature of document scope bookmarks to accomplish the exact same thing. Now we're right about back on track for time. So sort of to summarize the presentation, the sandbox, even though it has a lot of issues, still does a pretty good job of keeping hackers from doing whatever they want inside of your system. I think after the slides from Ian's talk hit the internet this afternoon, there's going to be a lot more people thinking of jailbreaks. I know I've been following the Project Zero bug tracker, and it's pretty exciting stuff. But in spite of all the issues that a sandbox has, it still does a pretty decent job of keeping you safe if you have all of your Gatekeeper stuff locked down. Specifically because the malware developers have to jump through all the extra hoops, even though we showed ways today of getting around Gatekeeper, getting around the jail, and also elevating to root, which gets you access to the kernel. It's still the sequence of each of those accomplishments that makes it that much harder for the bad guys to succeed. Wanted to thank a bunch of these guys for having such cool content that I learned from for this talk. And yeah, thanks. Any questions? No? Thanks, guys.